So we're going to move on to our fifth note on modern atomic theory. So we've talked about the history of the atom, how it came, our current understanding of the atom came to be by looking at various scientists over the course of history. And right now we're going to begin talking about Bohr, because I think you're fairly familiar with Bohr's model of the atom, the solar system model, and I believe that is what your current understanding is of the atom and what it looks like, right? So in grade 9 and 10, we teach you that electrons exist in these orbits or these energy levels around the nucleus. So in the nucleus here, we would have protons and neutrons, and then the electrons would be in these sort of circular orbits surrounding that nucleus, right? And we taught you that, there's the first, second, third, fourth energy level. Sometimes you may see the energy levels referred to as K, L, M, or N. So if that shows up somewhere, you'll know what that's about. But again, that's referred to as the solar system model. Now, there's a lot of validity to the solar system model of the atom. It helps us make a lot of predictions about certain characteristics of atoms and elements, but it's incomplete and not entirely correct. So hopefully today through our discussion, I'll be able to point you in the right direction so that you have a better understanding of what electrons and atoms are actually doing. Before we go into that, though, I want to discuss a few points that are, true for both models, both Bohr's model and our current understanding of the atom. And I want you to pause the video to really think about what the answer to this question might be. Okay, so first of all, let's go through this. So the farther the orbit from the nucleus, in other words, the further the electron is from the nucleus, the higher the energy required by the electron occupying it. So my question to you is why? Why is it that an electron way out far from the nucleus is going to have more energy than an electron in a lower energy level? Well, hopefully you've had time to think about it, and I'm going to help you think about it by looking at this picture here, right? So we know that the nucleus contains positively charged protons. So our nucleus contains protons and they're positive. And our electrons are negatively charged. So if you're an electron and you're negatively charged, you're really attracted to the nucleus right here. You really want to be close to that nucleus. The only way that you could possibly move away from that nucleus is to have energy. It takes a lot more energy to move away from that positive pull of the nucleus. So it stands to reason then that if you have an electron way out here away from the nucleus, that it's going to have gained a lot of energy and would have to possess a lot of energy to exist out there. So give yourself a round of applause if you were correct with that. Now I'm going to talk about this next little bit, which is that the electrons can move from one level to another but cannot exist between levels. So that is sort of, I usually try to explain that by discussing, well, it's sort of like climbing stairs. You can't climb half of a stair. You're either climbing the whole stair or none at all. And it's the same for electrons. Electrons can either jump from the first to the second level, but they can't exist anywhere in between, according to Bohr's model. Okay, remember this is all in relation to Bohr's model. So along with that come a couple of important terms that I want to talk about. The first is transition. Okay, so when you're transitioning, it means you're moving from one thing to another. So what would be transitioning? Well, the electron. We're talking about the electron jumping to a higher energy level, okay, when it gains energy. Okay, we can also talk about it coming down, but it can transition from a low state to a high state, but it can also transition from a high state back down to what we call the ground state. Well, what is the ground state? That's really where the electron would normally want to be if we weren't adding any extra energy to it. So That's just your regular old atom sitting around. Nobody's shining light on it. Nobody's pumping electricity through it. It's just sitting there. Where would that electron be? Okay, that is what we call its ground state, and it's where that electron is going to be most stable. Okay, a couple more things that I want to talk about around transitioning and electrons transitioning between energy levels. Notice, and this may be a topic that you're able to cover in grade 10 science, which is that when you add energy to an atom, then what that does is it excites the electrons, and the electrons have the ability to move to a higher orbit, right? So for instance, solar energy, electrical energy, any form of energy will help to excite those electrons, and maybe, if it's the right amount of energy, cause it to transition to a higher orbit. Okay. Now the problem is that if that energy cannot be sustained, then the electron cannot sustain its position away from the positive pole of the nucleus. And so what happens as a result is that the excess energy gets emitted. Right? That's what this little red arrow here, now green arrow, is trying to show you, that energy would be emitted as light, and often depending on the transition. So in other words, which energy level you're moving to or from, okay, or back down to, then you're going to see light of a different color, which is pretty cool. So Bohr did some experiments with hydrogen. Hydrogen, if you look at it on the periodic table, it has an atomic number of 1. So hydrogen has an atomic number of 1, which means that it has 1 proton. And because it has 1 proton, he was able, and 1 electron, so it's the electron that's actually more important here, he was able to do some experiments showing what happened when he added specific quantities of energy to a hydrogen atom. And so what he was able to create from that is what we call a line spectrum. So I'm going to explain a little bit more about this in another diagram. But the line spectrum is this thing right here where you see the black in the background and then you see lines of varying color. So the lines basically are representing different types of transitions that one electron will be making. And that's dependent on the amount of energy that would be added and then released to that atom. Let me show you a little bit more about what I mean. So I can see that the diagram is a little bit faded. I'm going to do my best to try and make you understand this. But in each of these cases, I have a Bohr-Rutherford diagram. And if you look really closely, what you'll see in each of the diagrams is a different type of transition made by the electron involved. So for example, in this diagram to the far left, I can see that I have an electron that would be in the, looks like the second energy level right here. So that's the second energy level. And that's its ground state. But somehow at some point it went up to the 2, 3, 4, 5, 6 energy level. And then it didn't have enough energy to sustain that and then went back down to its ground state. When it went back from the 6th to the second energy level, it looks like it emitted light that was, followed the electromagnetic spectrum in terms of that violet color. So in each of these examples, what you're seeing is a different transition. Here I'm seeing an electron go in the second diagram over. I can see it says the 5th energy level to the 2nd, right? And there's my indigo light, and so on and so forth. So in each of these examples, you're seeing the electrons make a different type of transition, and based on that transition, we're seeing a different color on our line spectrum at the top. So not to worry, you're not expected to know the order of these colors or which transition produces which color. That's just information. I want you to understand why the line spectrum, how we arrived at getting the line spectrum, and it's all based on the different types of transitions that can occur, and each transition producing a different color of light. Okay, so one last little bit that I want to talk about is this term atomic emission spectra. So basically, when you, like we were talking about, when you pump light or electricity through that element, then you're going to see those different types of transmissions. So the emission spectra is just the whole spectrum of color that you see when that happens, right? And that's going to be, the interesting thing about that is it's kind of like a fingerprint for the element, because each element will have its very, very own spectrum. And if you were to do this type of activity with an atom other than hydrogen, you would see a completely different array of colors. And that would be, like I said, that would be a good way for you to identify the elements, similar to a fingerprint. Okay, so this is where things get tricky, because it turns out that Bohr wasn't really right about the whole orbit thing. It was a pretty simplistic view, and so Schrödinger and Heisenberg, who were two scientists working in the 1920s, late 1920s, developed a different model of the atom based on more current evidence, right? So, and that model is based on quantum theory. And so what they were able to develop are a series of equations that basically depict the boundaries within which an electron can pass. And so instead of electrons existing in orbits, they sort of envisioned the electron being sort of in a cloud. Okay, so and I'm going to talk a little bit about this. So they talked about, well, why is it that electrons, if they're moving around in an orbit, why are they not losing energy and crashing into the nucleus, right? So they describe them as being in these electron clouds, which are regions of where the electrons might have a higher probability of being. So let me explain that. You can see there are some more sort of opaque regions in this diagram here, and near the fringes it starts to get a little bit more translucent, and then you don't see any white past that. So basically the area where it's most opaque is describing statistically where the electron is more likely to be. And as you move farther and farther out, you can see the electron is less and less likely to be in those zones. So depending on the electron, and depending on the atom, and depending on the energy level within that atom that electron is occupying, the parameters or the shape of where that electron might be will vary just a little bit. Okay, so as before, we always refer to electrons that are in the outer energy level, the highest energy level, as valence electrons. So that's still true whether we're talking about the electrons being in orbits or in these electron cloud configurations, right? The electrons that are in the highest energy orbit are still going to be referred to as valence electrons. So I want to give you guys a bit of a picture of this so that you can visualize it. I know this is a little bit tricky. By the way, we're not going into a whole lot of detail this year about this. This is a grade 12 concept. In grade 12 we'll go through this in much more detail, but I do want to give you a better visual so that you understand this moving forward. Okay, so here you can see they're phasing in and out. So ancient model of the atom, moving into the Bohr-Rutherford diagram, sort of Bohr model in orbits, and then back to our electron cloud model. I'm going to go and I'm going to show that again. So we're going to go through this again. So current model of the atom, you can see that this red ball right here is representing our nucleus. And then on the outer part here, we can see that the electrons are moving around. So what I want you to imagine is that you only have one electron, and every time it moves to a new position, it's almost like it's dropping a little piece of ink behind and just dotting where it's been. And so it keeps moving and moving and moving, and every time it's kind of depositing this little ink dot showing where it's been. Okay, so remember that we had, Dalton understanding that atoms were in constant motion. Then, based on the work of Rutherford and Thomson and Chadwick, Bohr came up with his solar system model, right, where the electrons are traveling around in discrete orbits. Now we sort of see the electrons moving around in that cloud.